Okay, here's the second video for the test review for test three. Couple notes I provided here. First off, no formulas are given, but all you need to know are the trig basics, including the Pythagorean identities, or just the first one, because remember, you can easily manipulate the others from there. And then the one double angle, as I wrote in the review, you do need to know the fact that sine 2x equals 2 sine x cosine x. That one shows up enough trig and calc that you might as well just start drilling that in your head now. So in this video, there are two major topics left, proven trig identities and solving trig equations. So let's look kind of at both of those. So solving a trig equation means you're trying to find the unknown. Okay, when you're proving a trig identity, you're not finding an unknown because it's saying all angles would work, okay, no matter what theta you put, well, as long as it's in the domain, right? Which sine and cosine, everything's in the domain, all real numbers, then both sides should be equal. When you prove an identity, you're not to mix across the equal, right? Because you're not solving an equation like you are in this example. Here, so therefore you only mess with the left-hand side or the right-hand side. Okay. The right-hand side, maybe you can do something, I don't know. Actually, maybe if you work with the right-hand side, you could do this in one step, taking a closer look at it. But most people see work to be done on the left and they choose the left. So I'm going to go ahead and choose the left. I was asked in class, is there an easy way, right, to do these? And yeah, there typically is. But is the easy way what you see right away? Not always. Okay. As long as you follow legit trigonometry rules, then you should arrive at the correct answer. It just might take you longer than someone else. All right, so looking at the left-hand side, I see fractions that need added, right? To add fractions, we need an LCD. The LCD is sine cosine, sine theta times cosine theta. So therefore, I need to multiply the left piece by cosine theta over cosine theta, right? Because that's just one. I'm not changing the equation, I'm just changing the way it looks. And on the this piece here, we need to multiply by sine theta, and then I could see like my denominator would match, right? Once I have that. So let's proceed. That looks good. Cosine theta multiplied by 1 plus cosine theta in the numerator, I will get, let's switch colors here, I'll get cosine theta plus cosine squared theta. Okay, all over cosine theta sine theta. The next piece I'll have sine squared theta over sine cosine, right? Cosine, sine, either way. Now again, we had an LCD, so we could have just combined the common denominator, right, all into one numerator if you wanted. But more so, what's to notice is anytime you see sine squared plus cosine squared, we know that that is 1. Okay, always keep an eye out for that. That appears often enough, and actually that will do it. Because notice we'd have cosine theta plus 1, and then, multiplying, we could do, we could reverse those. So all I did is worked with the left-hand side, and it now matches the right-hand side. We are good. We proved that that crazy identity we started with is in fact true. So I'm going to jump back and forth between an equation and identity. On the right, we have an equation. Okay, I'm trying to solve. I'm trying to get x. Think of, back in algebra, I know I have cosine squared, and I'm just writing x squared, but the concept, the idea is the same. I need it to equal 0, right? When you're solving an equation, we're trying to get 0, unless it's linear, right? Then you could go straight for x, or if you only have one variable, I should say, you could just solve for that variable. But when you have two, you need to get it equal to 0. That way you have the zero product property. Remember, the zero product property says when I multiply two things, any two expressions, right? Does that just be a number? And I have 0. One of them has to be 0, or both. That's your goal here. All right. If you only have a single trig expression, like I have here, cosine, right? We could think of it like I wrote above, x squared plus 2x, and then just subtract 3, or just rewrite that, minus 3 equals 0, and factor. Usually we don't make a u substitution, but you can if you want. Okay, if you want to write u as cosine x and then factor, that'll work. But by factoring, we have cosine multiplied by cosine will give us cosine squared. Then I have a positive 3 and a minus 1. That would create negative 3, and that when I check inner and outer, right, I do get 2. Somebody had asked, well, what if I'm terrible at factoring? I would hate to do it, but you could use quadratic formula, right? X equals negative b plus or minus. I'm not going to write it out. You know the quadratic at all over 2a, and do it that way, but what a pain that would be. All right, so now that we have it factored, we know either this is 0 or this is 0, which means cosine x is negative 3 or cosine x is 1. Okay, we could do cosine inverse on both sides, but you know, unless if it's special angle, you should be able to use the unit circle anyways. Now, cosine x is negative 3 will never happen, right? That is outside the range or the domain of the inverse. We can't do that. So this yields no solution there. But when is cosine 1? So remember, cosine is x, right? So when is cosine 1? Well, that would only be 1 point. That's when x is 0. Now, technically, because it's periodic, that also means it could be 2 pi, it could be 4 pi, or any multiple, right? But all I'm going to ask for is solutions that are on the unit circle, one full period, 0 to 2 pi. So just give me those solutions and we'll call it good. So therefore this only has one solution, that is x equals 0. And you could plug that in your calculator to make sure that's true as well. I'm going to skip that part. Okay, then the next one I didn't want to show, sometimes you could see a trick and actually do it in one step, and it's nice and easy because if you have one divisor, you can split that up to cosine over cosine, and then plus sine over cosine. And we are actually done because this is 1, right? And sine over cosine we know is tangent. One step, done. If your denominator, like if these were flipped, you cannot split it up like that, right? It only works with one divisor, and we could quickly see too, like as a check, they have an LCD cosine, so I could add the numerators, right? Where if those were flipped, you cannot split that up because adding fractions, I need an LCD, and if I were to split that, now I'd have to multiply to find the LCD like we did above. Doesn't work. All right. I have a couple more examples of identities, but I did want to show sometimes they are quite easy, right? If you catch it. All right. The next one, sine 2x. You can't factor anything because we have a sine and a cosine. And in fact, we have a double angle. and that yields that formula that I'm asking you to memorize. That is equivalent to 2 sine x cosine x. Okay, so that comes from the double angle formula. I'll just write dA, double angle. Now you could factor. Always, when you factor, right, don't immediately jump to this. Always look for the GCF first. If there's a GCF factored out, it will make everything much easier. So we have a GCF because I have cosine and cosine. Factor that out. What are we left with? We're left with 2 sine x and then plus 1, right? I need that placeholder. So therefore this equals 0, cosine x is 0, or 2 sine x plus 1 equals 0. And when is cosine 0, we would have two solutions on 0 to 2 pi, because x is 0 here, it's pi over 2, and x is 0 down here, right? 3 pi over 2. For the right-hand side, that subtract 1, divide 2. When is sine x negative 1/2? Remember, sine is y. So that would be this angle here, which is 7 pi over 6. And then this angle here, which is 11 pi over 6. So we have 4 solutions to that equation. And again, you could check it. 4 solutions in 0 to 2 pi. There are infinitely many, but in one full period, those would be our solutions. All right, couple more here. So how about let's prove this identity. Okay, there's an example. Let's do one more. How about this one here? Tan y plus cotangent y over cosecant y equals secant y. All right, 2 different tricks here. So first off, again, there are more than one way to approach this, but I see a bunch of squares. I should instantly be thinking Pythagorean identities, right? I had said, really, you just need the sine squared and cosine squared because you can manipulate the others. And in fact, with this one, the approach that was suggested in the class was this. And I agree. Why not make secant 1 over cosine? And if you see cosecant 1 over sine and tangent sine over cosine, that's a great trick to do. Okay, so let's do that. And also because I see this on the outside, when I distribute, they'll cancel, right? Now, one other thing, you don't always have this, right? You don't always have sine squared plus cosine squared. For instance, now on the left-hand side, I see all cosine squareds, right? So why not manipulate this one to cosine squared? Again, you don't have to. I mean, there are many ways to do this problem, but that is an idea. So sine squared is equivalent to 1 minus cosine squared, right? Just subtract that to the other side. Don't forget your negative out front though, right? The negative, and then 1 minus cosine squared. Okay, then let's check it out. We should be about done, honestly. Cosine squared times 1 is cosine squared on the left. Those cancel, so we get minus 1. And if you distribute that negative, we'd have negative 1 plus cosine squared. I didn't interchange the left and right hand side, right? I worked with them individually. And I end with an identity. Done. All right, since we were talking about change in secants and cosecants and tangents and cotangents, I decided to share one more example in which I would change all of these. Okay, again, it's not the only way, but I would just change tangent to sine over cosine. Cotangent, cosine over sine. Cosecant is 1 over sine. And I would even do the right, 1 over cosine. That's what my goal is. I'm hoping I end with this right-hand side by manipulating the left. With all these fractions, let's clear it, right? Multiply everything by the LCD. I have sine y, cosine y. But we can't just magically multiply something, but we can multiply by a form of 1. Since that is 1, let's go ahead and distribute. We'll do green here. When I multiply there, cosines cancel, right? So I get sine squared, which we like. Distribute here, sines cancel, so I get cosine times cosine. We like that even more. Sine squared and cosine squared is 1. I could already see that 1 on the numerator. Okay. When I do the denominator, sines cancel, so I just get cosine. So are we done? Yep. Numerator is 1, denominator is cosine y, which is secant. Done.